We can go.
All right, great. Thanks, David, for the introduction and for the invitation to speak here. And let me just echo what you were saying about interrupting me. I'll try to keep an eye on the chat window, but I might not see it. So please feel free to speak up if you have questions. Okay, so I want to tell you all today a little bit about some ongoing joint work with Brent Nelson, where we're studying this thing that we call free Stein dimension. And very largely speaking, it fits into the zoo of regularity properties for von Neumann algebras and free probability. But let me begin by giving you a little bit of the context we're going to be working in. So throughout the entire talk, the context will be that of a non-commutative the context will be that of a non-commutative probability space, or W star, non-commutative. And so what that means, probability space. What that means is that we have always a von Neumann algebra M and a tracial state. And these are just going to be standing assumptions throughout the talk. And so, but why is this thought of as a non-commutative probability space? I mean, I'm sure many of you have seen free probability talks before, so this is not a mystery. But the idea is that this is a generalization of commutative von Neumann algebras like L infinity of some probability space together with some measure and a functional given by integration against that measure, which is a tracial state, tracial for free because it's commutative. Another example is the n by n matrices with the normalized trace. And a third example would be the group von Neumann algebra of a, say, countable discrete group gamma together with testing against the point mass with identity, the standard trace. Okay. And so it becomes useful a lot of the time in free probability theory to think about the elements of these operator algebras as being some sort of non-commutative random variable. And that's the setup we're going to be working in. So we'll always fix, again, we'll have fixed some tuple x, say x1 through xn, of self-adjoint elements of M self-adjoint. Okay, and we think of these as, here goes my stylus. We think of these as non-commutative random variables. And the goal, broadly speaking, is to say, can we ask probabilistic type questions about x1 through xn, about, say, their distribution, and from that learn interesting operator algebraic properties of the von Neumann algebra they generate? So we want these to generate M. Goal. Can probabilistically flavored properties X tell us about M. Okay, and this is an enterprise that has been in development under study since the 90s, when Dan Voiculescu introduced a series of papers about the analogs of entropy and Fischer's information measure in free probability. And it turns out that there is quite a lot that can be said. And let me just highlight two example results, which broadly speaking follow the same philosophy, which is that if you have something nice about the generators X, you should learn something nice about the von Neumann algebra they generate. And so without telling you exactly what these mean, it's true that if the modified free entropy dimension of the tuple X is strictly larger than 1, then as a consequence, we learn a few things about M. So M will have no Cartan subalgebra. It will be non-gamma. And it will not be prime, and it will be prime, sorry, is prime. I guess I missed an is here as well. Okay, so which is to say it does not decompose as a tensor product of two infinite dimensional fundamental algebras. And these results are due, the first two items are due to Voiculescu, and the final one is due to Gay. Okay. And another series of results is that this other version of the free entropy dimension, attaining its maximum value of n, one consequence of this, due to recent work of Mai, Speicher, and Yin, is that the tuple X then has, and I'm paraphrasing a little bit, has no non-commutative rational identities, which actually is saying that the free field, or the free division field, the free skew field embeds into the affiliated operators on M. I'm going to run out of space. Mai, Speicher, Yin. Oh, wait. Okay. And so again, both of these are telling you something that if you have some sort of free probabilistic assumption about the generators, you get some nice and powerful results about the fundamental algebra they generate. And broadly speaking, all the work in free entropy theory divides into one of two camps, one of two approaches. The first is the so-called microstates approach, and that's where this delta zero lives. And roughly speaking, there the idea is that for a set of generators to be nice means that it can be very well approximated by matrices, by matricial microstates. That the tuple has a lot of valid matricial microstates. Of course, there's a big obstruction to this one, which is embeddability. If your tuple of generators form a von Neumann algebra which doesn't embed in our omega, then there will be no microstates, and so the entropy will tell you nothing. And as we know from this recent MIP star equals RE result, it turns out that there really are von Neumann algebras that are not embeddable, and so the free entropy, or sorry, the microstates version of the picture can't possibly tell us everything. And the other approach is illustratively called the non-microstates approach to free entropy because it does not use microstates. The idea, roughly speaking, is that here we want to see how well behaved the x's are under free differential calculus, very roughly speaking. That if the variables are well positioned, it should be possible to do something that looks like calculus with them, essentially speaking. And let me talk a little bit about the motivation behind this before I dive into the free side of the picture. And so the motivation for the non-microstates approach is Fischer's information measure, which is a quantity of statistical importance, I guess. And very roughly speaking, Fischer information of a variable, just an honest classical commutative random variable x. And what this is supposed to tell you, so what it measures how much you learn about about how much you learn about the mean of x from one measurement of x, assuming that you know the distribution of x minus its mean. Okay. And so what you should say, essentially, the smoother the distribution of x, the less you learn by measuring its mean once. So if x is, say, a Bernoulli random variable that takes on one of two random variables, if you get a single measurement, then suddenly you've narrowed it down from an infinite possible number of distributions to just two. Whereas if x, it has a much smoother distribution, like the bell curve, it's a normal random variable, and you measure it once, you have, your measurement becomes the best guess for the mean, but you still, there's still a lot of uncertainty there. And so Fischer information being low corresponds to having a nice smooth distribution. In terms of how it's actually defined, for a single variable, it's given by the L2 norm of the adjoint of the derivative as an unbounded operator acting on the constant function 1 within L2 space of the probability measure of x squared. Okay. And remarkably, it turns out that, I forget the attribution on this theorem from the 70s or so, that this Fischer information quantity can also be related to entropy as the time derivative of entropy as the variable x is perturbed by an independent Brownian motion. Okay. So that sort of motivates the whole beginning of the approach to non-microstates free entropy theory, which is we're going to try to take this setup, find the appropriate analog of the adjoint of derivative, which causes problems for us because, of course, with non-commutative random variables, we're not acting on an honest space anymore. We can't take actual derivatives. And then if we integrate that, we can call the resulting thing free entropy. So unfortunately, so the question is, the most important question to answer, what should play the role of ddt star in the non-commutative setup? And so those, and it turns out that the right thing to do the job are the free difference quotients. Everything I've said so far goes back to Voiculescu in 97 or 98, his fifth microstates, or his fifth free entropy paper. The free difference quotients. So what are these? These are derivations defined on the algebra generated by x1 through xn, which take values in its tensor square. And they are defined by linearity, the Leibniz rule, and the condition that if I take the ith derivative of the jth variable, I should get 0 unless I equals j, in which case I get 1 tensor 1. Okay. And so why are these thought of, why do I call these difference quotients? Well, let me give you two quick examples. So the first is if I take, say, the second derivative of x2, x3, x2, x4, then I get two terms surviving, and more or less what the derivative does is every time it sees a matching variable, it replaces it with a tensor sign. So we have one tensor x3, x2, x4, and x2, x3, tensor x4. And you can just sort of repeat this exercise forever. But why is this called the free difference quotient? It turns out that if I have a single variable, then taking the derivative of p of a single variable x1 gives me precisely p of x1 tensor 1 minus 1 tensor p of x1 divided by x1 tensor 1 minus 1 tensor x1. So it really looks like a difference quotient. Okay. So let me also mention that at this point, what I'm saying doesn't quite make sense if the generators of my von Neumann algebra admit algebraic relations. If there's some identity within the polynomials in those variables, then I won't be able to define the free difference quotient because the identity will need to both be some polynomial that's some sum of polynomials, and the tensor product is not 0, but also 0. And so, but it turns out we can get around that, and I'll explain how in a little bit. Yeah, okay. So it turns out that these free difference quotients play the right role of DDT, and so the free Fischer information is defined. Oh, okay. No, sorry. Let me say one more thing. Having defined these, it's also useful to introduce the operators, just the free gradient, which acts on a single polynomial and spits out a tuple by taking each derivative, and the free Jacobian, which is defined by if I take the Jacobian of a tuple of polynomials P1 through Pn, then what I get out is the matrix whose ijth entry is the jth derivative of the ith polynomial. Okay. It turns out for technical reasons, these are useful things to consider. Okay. And now we want to, so our goal is to find the right analog for the adjoint of the derivatives. And so if I view each of these free difference quotients, or the free gradient or the free Jacobian, as unbounded operators defined on the polynomials sitting within the appropriate L2 of M or L2 of M tensor M space, then these give me nice unbounded maps into the tensor product of L2 M with itself for the appropriate matrices or tuples. And so I can take their adjoints there. And so we get adjoints to these unbounded operators. And this is also the step where it turns out I can get around the fact that the free difference quotient may not be well defined. Because even if it's merely a relation rather than an honest function, if it takes multiple values on some polynomials because of identities, I can still write down the defining equation for the adjoint, right? So what would that ask? To say, for example, that the adjoint of delta I applied to some element eta in the tensor product is a vector C in the L2 space. Well, that is just saying that for all A and B, which are in the relation delta I have the inner product of B tested against eta, which sits inside L2 of M tensor M, or which is an inner product within L2 of M tensor M, should be equal to the inner product of A against C. And if the partial derivative is an honest function, then this is just the usual definition for adjoint. But if it's merely a relation or a multi-valued function, well, this is still something you can make sense of and then define the adjoint that way. So that's how we get around that little hiccup. Okay, but so how does this, where do we go? What do we do now that we have these things? Well, if I let this blackboard 1 be the matrix, the diagonal matrix whose diagonal is given just by one tensor 1 everywhere, zeros on the off diagonal. And this is an element of L2 matrices. This is an element of n by n matrices in L2 of M tensor M, or M tensor M off if you prefer. Okay. Then if, or we define the free Fischer information of the tuple X, by we, I mean Voiculescu defines the free Fischer information of the tuple X to be the L2 norm of the adjoint of the Jacobian applied to this one tensor 1 matrix squared, if 1 is actually in the domain. And infinity otherwise. Okay. And it turns out that, let me mention just quickly a couple ways that this is useful. So the free Fischer information, for example, is minimized amongst variables of a given fixed variance by a free semicircular family. And so you can test that. It's also true that, for example, if if the variables admit any algebraic relations, then that automatically forces the free Fischer information to be infinite. So already it's telling us, already it can be used to learn a lot about the von Neumann algebra M. But it turns out that it can be challenging to work with. It can be difficult to tell if one is actually in the domain of this operator. And so, and it's a very powerful result when it is. And so what Brent and I have started to ask is, can we weaken this condition a little bit? Can we ask for a little bit less? Rather than saying we want to have one tensor one in the domain of J star, what if we only want it to be close to having that property? And we define, motivated by all this stuff, the free Stein dimension we denote by lowercase sigma of x, and it is defined to be the dimension as an M tensor M op module of the domain of the free gradient closure. And this always takes values in the range from 0 to n. And I'm sweeping under the rug, for example, the fact that the domain of the gradient is actually an M tensor M op module, but that can be checked with sufficient algebra, I suppose. And so it's not necessarily obvious how these things are related, aside from having something to do with free derivatives. But one thing to note is that if one tensor one happens to be in the domain of the free Jacobian, then that can be used to show, that can be used as a starting point to show that it's because it's closed under as a module, that this domain has to actually be maximal within L2 M tensor M to the n, which is the space it lives in. So as soon as you have finite Fischer information, you can show that this quantity is maximized by moving it around a lot. But it's possible that there's some obstruction to conjugate variables existing, and this measures sort of how close you can possibly come in a certain sense. Okay, and so one of the very useful things that we were able to show about this quantity is that it actually is an algebra invariant. Not a von Neumann algebra invariant, just a polynomial algebra invariant. But that's quite nice because there are those things can be quite tough to show when you're working on the non-microstate side of things. And let me sort of sketch the underlying very useful observation for that is that if we consider this space that we've termed der one tensor one of the algebra of polynomials of x, so this we define to be the set of all derivations from C of x into L2 of M tensor M op with the property, well, so D is a derivation. I prefer actual blackboards because you don't run out of space as quickly. And also I want one tensor one to be in the domain of the adjoint of anything in this set. Okay. So on the one hand, this set of nice derivations does not depend on the generator's x on the polynomial because it's merely defined as maps on the polynomial algebra. And if you picked a different set of generators, well, you would have the same set of valid maps, the same set of valid derivations. But it turns out that this, once you've picked a set of generators, you can map this set into the domain of the
Ian, there's a comment in the chat from, or a question from Ulrich.
So
Can you see it, or should I read it out?
You can actually, yeah, I see it. The question is on the domain, on the definition of free Stein dimension, whether it should be the domain of J star as opposed to C star. And it turns out that the two both are modules, and they're related simply by a factor of 1 over n. If you put the free Jacobian here instead, still taking the closure, and you normalize by, oh no, there we go. I need a little more space so that I can write over 1 over n here. Then these quantities are equal. But it's just for technical reasons, it's often nicer to work with the domain of partial star rather than the domain of J star. And more or less, you can see that it's basically translating between the domain of J star and of partial star amounts to taking just a list of n things that are in the domain of delta star. You can go back and forth very easily, but for technical reasons, it's a little nicer to work with partial star. Okay, yeah, thank you. So where was it? Right. One of those technical reasons is that it's quite easy to relate this set of nice derivations to the domain of partial star for a particular set of generators once you've picked them. And what you're going to do is, given any derivation here, D, it gets mapped to the tuple where you simply, well, where you almost simply evaluate it on each generator, dx1 through dxn. But then you need to apply the Tomita conjugation operator, which is a non-script J. It turns out that this is, it can be shown that this is a bijection between der1 turns to 1 of Cx and the domain of the free gradient. And you can also show that it intertwines the modulo action on the space der1 tensor 1 with just multiplication on the domain of delta star. And so I should mention, right, the problem, the technical issue with working with the space of derivations is that there's not a good norm on it. It doesn't have a Hilbert space structure. And so it becomes, there's not a nice notion of dimension there, whereas the domain of partial star has a notion of dimension. But the fact that this sort of intertwines the actions just of polynomials means that with a bit of work, you can, if you had a different generating tuple, delta y, then you could pass up to this space of nice derivations and back down to der tensor x. That gives you a map between here, which is a bijection that intertwines which intertwines polynomial modulo actions. And then you can upgrade that to saying that this is actually a module isomorphism of their closures with respect to the von Neumann algebra action. And that exactly is enough to tell you that the dimension of one space is the same as the dimension of the other. And so this is how we show that this thing is a polynomial algebra invariant, which is quite nice. Now, let me also, oh yeah. It turns out that sort of viewing this picture, viewing this set of der1 tensor 1 turns out to be a very useful thing for us to work with because it has a lot of expressive power, I suppose. And so one of the things, another thing that you can realize, well, so, okay, let me record the theorem that I said out loud, which is that sigma of x depends only on the polynomial algebra generated by x. And so if you pick a different set of generators, you'll get the same Stein dimension. Okay. Another proposition that you can get by sort of working carefully with this space of derivations, and I'm not going to show you the gory details, is that if M contains a diffuse element, is diffuse, then as a result, the Stein dimension of a generating set of M has to be at least 1. So we have a nice lower bound there. And we have some, turns out that this can be pretty useful for actually doing computations because it gives us a lower bound to work with. And then usually we can exploit structure of the algebra that we're working on as well to find an upper bound for things. And so recently, and this is part of our ongoing project, I'll call this another proposition, I suppose. You can use this lower bound and some careful working with this space of derivations. And in particular, one can look at how relations in the algebra generated by X translate into restrictions on the space of derivations from which have 1 tensor 1 in their adjoint. And that can be used to actually compute explicitly the Stein dimension in several nice cases. So for example, we know that the standard generators of the irrational rotation algebra, there we go. Have Stein dimension 1. Free Stein dimension 1. As a brief aside, let me mention that every time I have said Stein dimension, that is an abbreviation of free Stein dimension. And I think Brent gets annoyed at me when I elide the free. And so you should imagine that I've been saying free many more times in this talk than I have been. Okay, so let's talk a little bit more going forward. I've shown you, I told you some nice properties about this Stein dimension, but it might be useful to actually know that it can be computed and maybe see some explicit examples of how that can be done. And so before moving into that, there's a related quantity that we've called the free Stein irregularity. And this is actually the thing we began studying first, and somehow it turns out we shifted our focus to be more on Stein dimension. But the definition, the free Stein irregularity is the quantity denoted by a capital sigma, star of X, which is the distance from, remember this diagonal matrix with 1 tensor 1 on the diagonal, to the domain of the free Jacobian, of the adjoint of the free Jacobian. And so this much more explicitly measures the obstruction of J star from having full domain. Because if the identity matrix is in the domain of J star, then that was what told us that the tuple has finite Fischer information, for example. That's where a lot of nice things happen. That's enough to tell you that the domain of J star is dense within all n by n matrices. And so this measurement is really saying, okay, how close are we to actually being in that situation where we have dense domain, for example? And right, as I said, when we came to this project, we actually started studying this quantity first, and later discovered that the Stein dimension was a more useful thing to look at in a lot of cases. But the two are related. I don't know, proposition. Exactly by the equation that the free Stein dimension is given by n, the number of generators, minus the square of sigma of X. But in a few cases, it can still be more useful to work with this distance to 1 measure. And I should mention that this distance is measured in the Hilbert-Schmidt norm on L2 of m tensor m. Okay, so one of the things that if you call something a dimension quantity, you expect there to be a certain subadditivity to it. And that is easier to establish on the Stein irregularity side. And it's true that for any tuple of X and Y, the Stein irregularity squared of x plus that of y is bounded above by their joint Stein irregularity with equality if they're freely independent. Okay. And the idea behind this one is you want to understand what the domain of the free Jacobian looks like. And just to sketch a picture of the proof, if I start with some matrix that is in the domain of the joint of the Jacobian of x and y, adjoint, which perhaps has entries A11, A12, A21, and A22, then the corners of this matrix are going to be in the domains of the respective free Jacobians. And so that allows you to get, you can get a bound on the size of the respective domains of the Jacobian for just x and for just y based on knowing how big the domain of the pair x and y is together. And if x and y are freely independent, then it turns out that anytime you have one of these so-called free Stein kernels for x and one for y, the matrix that simply puts them on the diagonal and 0 on the off-diagonal entries is going to be in the domain of the joint Jacobian adjoint. And so those sort of computations allow us to have nice bounds on how these things work subadditively. And of course, because the free Stein irregularity and obstruction to nice regularity has opposite sign to free Stein dimension, that tells you that you get the opposite subadditivity for Stein dimension, which is nice. Another thing to mention is that the free Stein dimension can be related to free entropy dimension, non-microstates free entropy dimension. I'll just call this one a fact. So if you have seen the definition of free entropy dimension before, then this will be meaningful to you. And if you have not seen it before, then just take it as the right-hand side is a quantity that is known to be interesting for telling you things about the distribution of axioms of unknown algebra they generate that has been studied quite a bit already. And because it's a regularity property, most interesting results happen as soon as free entropy dimension is either strictly larger than 1, or as soon as free entropy dimension attains its maximum value of n. And because we have a lower bound from free Stein dimension, that allows us to bootstrap a bunch of results that are already known for free entropy dimension into free Stein irregularity. So at the beginning of free Stein dimension, at the beginning of the talk, for example, I mentioned that maximal free entropy dimension means that there are no non-commutative rational relations amongst the generators. And well, because maximal Stein dimension implies maximal free entropy dimension, that tells us that if you have maximal free Stein dimension, you get this result as well, that there are no rational non-commutative relations among the variables, which is nice. For people who've seen this before, let me just mention as well that I put a 6-pointed star here, and of course it's also true for a 5-pointed star because the 5-pointed star free entropy dimension is larger than this pointed star free entropy dimension. But and in every case where we're able to compute both quantities in this inequality, they're equal. And if one was feeling particularly bold, one might guess that they're always equal. But this, I think, reflects more on the difficulties involved in computing either of these quantities explicitly. And so, this relation lets us also do an explicit computation of this quantity in at least some setting. So the last thing that I want to talk about today is actually showing that you can how in some cases this can be explicitly computed for a single variable. So for a single variable x, the Stein dimension of x is given by 1 minus the sum over real numbers of the square of the atom of x at that real number. So of course here mu of x is the spectral measure of x with respect to the state on the von Neumann algebra that's lurking in the background that we're working with. And to briefly give you an idea of how you actually honestly compute something like this, well, we have from this relation with free, it's known that this quantity on the right-hand side is exactly the free entropy dimension of a single variable. And so we have an upper bound on Stein dimension based on that relation. And so we only need to bound it below to actually compute this value. And bounding Stein dimension below is the same as bounding Stein irregularity above. And so really our goal is to show that the Stein irregularity is bounded above by this sum over atoms in the spectral measure. So we want to show that the Stein irregularity of the single variable x squared is bounded above by this sum over real numbers, size of the atoms squared. Okay, and so that can be done just by writing down an explicit element in the domain of delta star or j star. Of course, for a single variable, they're the same operator. Okay. And so how do we do that? Well, it turns out that one can just find explicitly something that is going to work well. So if you start with the map, right, x minus y, or well, sorry, let me just mention here that I'm going to realize L2 of m tensor m. So what is this? This is a tensor product of two von Neumann algebras in a single variable. So we're in the commutative setting. So these are honest functions on the spectrum of x tensor x. And I'm going to realize this as functions in two variables, x and y. So rather, let me just write x for x tensor 1 and y for 1 tensor x. Which, bad notation. Okay, so we want to find something in the domain of the adjoint. And it turns out that if you look at the quotient of x minus y divided by x minus y squared plus epsilon squared, then it can be shown that this is in the domain of the derivative with respect to x adjoint. And that just comes down to doing a computation, right? So how do you check that something is in the domain of the adjoint of the pre-difference quotient? So you want to essentially try to do integration by parts. And so what you want to check is that the integral of x minus y over x minus y squared plus epsilon squared times well, or rather, sorry, I've made a mistake. Okay, rather than try to do the computation in front of you, rather than trying to do the computation live, and especially given the fact that I have only 2 minutes left in the talk, let me just remark that it winds up being just a straightforward computation. And on the other hand, if you ask what happens to Oh, I think I dropped a square, which is part of why this isn't working. There we go. Right. Yeah. Okay. And so you can do the computation, and this will work out. It will be in the domain. And on the other hand, if you look at what happens as epsilon tends to 0, these elements in the domain are converging to the characteristic function of the off diagonal. Right? So these things are converging to the characteristic function of x not equal to y, right? Because as epsilon tends to 0. And then if you ask what the distance is from this characteristic function to 1, the function that is 1 everywhere, well, the difference between the two is supported on the diagonal. And so what you're really computing at the end is the square of all the atoms. And so just by sort of being smart and writing down something that happens to be one of these free Stein kernels, you can explicitly find the distance and compute the Stein information, the Stein dimension and the Stein irregularity. And then this also leads to a bunch more, because once you can do it for a single variable, and when you know it's additive across free things, then this tells you that you can compute for any free tuple of generators. So we can find explicitly the Stein dimension for n freely independent semicircular variables, for example, has to be maximal, has to be n. And this, yeah. And so it turns out this has been a very useful thing, and we're continuing to. It's an ongoing effort to investigate what can be said about when Stein dimension is full or when it's greater than 1, and we're continuing to investigate and hoping that more can be found there. But I guess I've reached the end of my time, so thank you for your attention.
Okay, thank you very much, Ian. So are there any questions or comments?